Okay, sorry. Okay, so we'll continue the discussion on MOC, the numerical method that is based on discretization and matching of the solution. And we are discussing the application of it in, I mean, it's restricted in visit flows. And the formulation that we have looked at so far is the one which is based on irrotational flows using the velocity, the potential function. But then it's also applicable to rotational flows. We have seen that because of the particular nature of the equations, the hyperbolic in mathematics, the hyperbolic partial differential equations, in a flow field, you can identify directions along which the derivatives vanish. The derivatives that we have considered them from the equation, from the specific governing equation, where the derivative of, say, u with respect to x, that is the x component of velocity with respect to x direction, vanish. And under such conditions, that is along directions where the velocity gradients vanish or they are indeterminate actually, the equations will get transformed. I mean, this is by the mathematical analysis of the equations. They, by equating the this one to zero, the u by dou x term to zero, the equation transforms to partial from partial differential equations to ODE. So then the transformed ODE, which is sort of made a set of algebraic equations by discretizing the domain, and that particular system of equations is what is solved. So that's a fundamental approach in MOC, the method of characteristics, which are applicable for both supersonic and hypersonic flows. So we have gone up to the discussion of the fundamental approach to formulate the problem, or and also identifying what is meant by characteristic. Okay, now just carrying forward the as already mentioned, the indeterminate nature at u equals a, that is along the characteristic lines, transforms the equation from partial differential form to a differential form of equations. So if you look at the way it is written here. Now instead of dou u by dou y by dou x, etc., we have dy by dx. It's a partial differential equation. Not only that, the way the formulation shows that the way it is formulated, it shows that it can be treated as a and actually this one with the degree of 2, for which we have the solution, the standard form of solution, where dy by dx can be written as, this is the standard form for the equations like second degree equations, minus b plus or minus root of v square minus 4ac by 2a, etc. So this can be transformed to such a form where we can rewrite the we can calculate the dy by dx. Now not everywhere, but along the characteristic lines, because only along the characteristic lines the differential equation becomes ODE. So along the characteristic lines, dy by dx can be calculated using the formulation similar to what is this one, that is for the equations of this type, where we have the standard what you call which comes inside the square root, etc. So such equations, obviously they will have two roots, one corresponding to the plus sign and the other corresponding to the second the minus sign. The two roots, because it's a binomial equation. Now remember that we are considering the characteristics passing through a point. So it should be available, sorry, it should be applicable along all characteristics. if you are considering a particular characteristic line there, we have the V, the flow direction, basically the tangent to the streamline if you are considering one. And then we have U, the tangential, the axial component of it, or the x-axis component of it, and Y, the y-axis component, V, the y-axis component of it. Okay, so U and V. Now, just by considering the trigonometry, the term can be what we have here can be written in terms of cos theta, sin theta, etc., which in turn can be further simplified. And also, if you see here, this term that is here, cos squared theta plus sin squared theta by sin squared mu is nothing but 1 by sin squared mu, and 1 by sin squared mu is sin inverse mu is mu is equal to 1 by m. So this cos squared theta 1 by sin squared mu can be written as 1 by m squared. M squared actually. Okay, so the dy by dx, that is, so what we are now talking about is the slope of the characteristics. Slope of the characteristics. So they can be determined using this relation. And if you look at I've just copied the same equation here from the previous slide. Dy by dx minus cos theta sin theta by sin squared mu plus or minus. This plus or minus is what gives two solutions. Two solutions means at the same point I can have two slopes, right? Which in turn means that at any given point A, you can have two characteristic lines. Okay, so at any given point you can have two characteristic lines. One will correspond to the positive side, the solution from the positive side, and the other will correspond to the solution for the negative side. And this in turn, the trigonometric function here can be further simplified as dy by dx is equal to tan theta plus or minus mu. That tan theta plus or minus mu. Again, this plus or minus indicates the possibility of the two solutions. So for any supersonic or hypersonic flow field, you can at any given point, at any arbitrary point that you consider, you can have two characteristic lines crossing that point or passing through that point. And the why the two characteristics, I guess it's obvious from what I have already mentioned. It's because of the possibility of having the two roots, right? And we also see that for when m is greater than 1, in the within the square root here you have cos squared theta plus sin squared theta by sin squared mu, which as a minus 1. As I mentioned, it's 1 by sin squared mu minus 1, which is nothing but m squared minus 1. So what you have here in the inside the square root is m squared minus 1. Okay, so you have a function of m squared minus 1 divided. So you have minus cos theta sin theta divided by sin squared mu plus or minus square root of m squared minus 1 divided by 1 minus cos squared theta by sin squared mu. So that's slope, and because of the two values, you can have two different solutions. You can have two different characteristic lines when m is greater than 1. Right? So when m is greater than 1, you can have two solutions for the function or two slopes. That is where you will have two different characteristics. So in supersonic flow as well as hypersonic flow, you will have two characteristic lines. Now when m equals 1, it's a limiting point. You can have one value which just corresponds to a solid flow. So when m equals 1, you will have only one value because the function here will become 0, or whatever you have inside the root will be 0. And for m is less than 1, square root of m squared minus 1, when m is less than 1, you don't have a solution for that, right? So as it is negative. So that's a reason why in subsonic flow you don't have anything like characteristics. So the approach of characteristics, the equations, governing equations in this form, because getting transformed to hypersonic parabolic equations, and when they have two solutions or two characteristics at any given point in supersonic and hypersonic flows, and the concept does not exist in in subsonic flow at all. So what we are talking about now is the method of characteristics is exclusively for supersonic and hypersonic flows. Okay, now physically, just to get clarity about why I just said you cannot have a solution for supersonic flows. You cannot have characteristics for subsonic flows based on the mathematical form of the solution, the mathematical argument based on the type of the solution. Whereas physically, why is that we don't have a solution in or why is that you don't have characteristic in supersonic flows? Just recall that when we say a characteristic, we said that it's a line across which the velocity derivative du by dx, or partial dou u by dou x, partial du by dx. So dou u by dou x is indeterminate, it's discontinuous, not u but the derivative of it. Okay, so now that is quite natural to have in supersonic flows and hypersonic flows. That is the velocity being abrupt changes, or rather the velocity gradient being discontinuous. And that is because the pressure disturbance is not felt upstream. And that a concept that we are quite familiar from compressible flow observations. That is in supersonic flows, hypersonic flow, when Mach number is higher than 1, pressure disturbance cannot go upstream. They cannot travel upstream because the flow itself is moving at a higher velocity than the pressure disturbance. So due to that, you cannot have discontinuities in velocity derivatives upstream. That is, if you say like situations like this. This is subsonic flow encountering a corner. And since the pressure disturbances are felt upstream, you will have the streamlines curving around upstream because the pressure disturbance is felt upstream, right? So this curvature of the streamlines, which ensures that there won't be such discontinuities and derivatives, etc., is that's a physical occurrence which reflects in the governing equations by the absence of having any lines or any directions along which there is any indeterminate value for velocity derivative. So that's a reason why it doesn't make sense to talk about method of characteristics in subsonic flow. Whereas in supersonic flows, we know that it's all quite dramatic. That is, the flow, when there is pressure disturbance, the flow goes through it and then adjusts, but there is no previous turn for the flow, right? And also please note that we are talking about characteristics, and what that I just highlighted, that just so that don't confuse the shock lines with the characteristic lines. Shock lines are lines of discontinuity. That is, even the say pressure, velocity, etc. The parameters themselves are discontinuous along them. Here in characteristic lines, the pressure, velocity are continuous, but the gradient, dou p by dou x, dou u by dou x, etc. are discontinuous. Yeah. So characteristics and shock lines are different. In supersonic and hypersonic flows, you have shock lines, you have as well as you have shock waves, shock fronts, you have characteristic lines also. Even in the absence of shock lines, you will have characteristic lines. So that is unique for supersonic and hypersonic flows. Okay. Sorry, any question about this, particularly this physical reasoning, etc.? Okay. So these two lines are usually referred to as left running and right running. Left running, right running. Actually, it's just a convention in gas dynamics and compressible flows to characterize the pressure waves. Need not be always characteristic lines, but usually we are mostly it is for characteristic lines. The waves are called as left running and right running. So if you look at this the figure that is shown here, you can see that at a given point, you have two straight lines which are crossing through it. You have a streamline which characterizes the flow direction. In addition to that, you have a left running characteristic and a right running characteristic. Now, this left and right, actually the terminology is sort of, it's just by convention. Actually, usually they say that if you are going along the, that is if you are going along the streamline and see that the flow is progressing towards your left side, or sorry, sorry, when you are going along the wave, that is why an observer who is moving around the along the wave sees the flow proceeding towards the left or right of that observer, is what they, is how it is named as right running or left running. So it's just a convention. Actually, there's nothing which should say, which says that it should be left or right, but that's how the two characteristics are identified. C plus for and that's also a convention. A plus sign is indicating left running characteristics, C minus right running characteristic. So, and they correspond to the tan theta plus or minus mu from the corresponding solutions. So this is how the streamline, the two characteristics at the point of consideration, they constitute the three lines of interest in the analysis. Okay, now this relation, that is d theta is equal to plus or minus m squared minus 1 divided into dv by v. That just comes from what we had listed. I'll get back to this equation before that I'll just summarize these 3 points about the characteristic lines. As of now, what we have discussed is 2D inviscid flows. They are applicable to 3D also, but what we have considered so far is 2D inviscid flows. And the governing equations are hyperbolic in nature, and characteristic lines are identified because of the hyperbolic nature of the mathematical equations. Now, the Mach lines, which correspond to the angle mu sine inverse 1 by m. That is what we can. They are the ones which along which dou u by dou x, dou p by dou y, etc. are indeterminate, and they are what we call as the Mach line. So sorry, as the characteristic lines. And for any given point, you can have such two such lines crossing, and we call them as left running and right running, corresponding to and usually denoted as C plus and C minus. Now, though the gradients are discontinuous, flow properties U, P, etc. are continuous along Mach lines. Now, this continuation of the properties, that this is something which we have even before we talk about characteristic lines, etc. We are familiar with the concept of Mach waves or Mach lines, and Mach lines are smooth transitions in flow. By the definitions of, they ensure or they are considered to be lines along which there is no finite discontinuity. So U, P, T, etc. are continuous along Mach lines. Okay, now we are just going to say this relation d theta is square root of m squared minus 1 into dv by v. D theta is equal to square root of m squared minus 1 dv by v, the same function. Now, we have seen this function earlier in Prandtl-Meyer expansion. Prandtl-Meyer expansion, recall, the flow expands over a corner along which a series of fans, a series of Mach lines indicate, actually, collection of the lines is fan. Okay, so a series of Mach lines induce the flow, the change in the flow directionality, acceleration of the flow is assumed to be an isentropic process. And in that, we have this Prandtl-Meyer function mu of m, which is derived based on the consideration of continuity, the constant or the isentropic nature, and the perfect gas behavior. So based on that, we have the Prandtl-Meyer function nu, which is an integral, and it can be integrated for across the fan, so that the integration will lead to the deflection, which can be calculated as a function of the Mach numbers before and after the expansion. This all carrying forward from the Prandtl-Meyer expansion. That is, theta 2 can be written as nu of m2 minus nu of m1, where m1 is the approaching mass flow, approaching Mach number, m2 is the Mach number downstream of the corner, or rather after the expansion. So the difference can be used to calculate the deflection theta 2. So now we see that the functional relation that we get from the Mach line is also from the method of characteristics also boils down to a form like d theta is equal to square root of m squared minus 1 into dv by v, which in turn means that if we integrate it, we can get the Prandtl-Meyer function. So Prandtl-Meyer function is done for a series of Mach lines along an expansion process, and the d theta formulation shows that they are identical. The two that we have for the characteristic line, or the flow field with the characteristic lines, is identical to the Prandtl-Meyer function, which in turn means that if you integrate it, you can get Prandtl-Meyer function, or you can get the results similar to the Prandtl-Meyer function. Now, this is how the function is denoted: theta plus nu of m. Please remember, we have the Prandtl-Meyer solution here. That is, theta 2 is nu of m2 minus nu of m1. In a similar way, the characteristic, the method of characteristics also follows the same way of solution, where the expression or the solution is expressed as theta plus nu of m, which is a constant. And a constant comes from the integration, and for a given characteristics, theta plus mu remains constant. So theta plus mu remains constant along one set of characteristics, and theta minus mu remains constant along the other set of. So we have a pair of characteristics, C plus and C minus. Along the C plus characteristics, theta minus mu remains constant, and along the C minus characteristics, theta plus mu, theta plus mu remains constant. So that's how the solutions are denoted in the characteristic plane. Now, based on this argument, or based on this method of or approach of solution, approach of formulation, the solution proceeds like this. I'll try to explain that with the sketch here. As mentioned earlier, we start off with some initial points where the values are assumed to be known. Whether we can either correct it during the iterative process, or we may probably have the initial conditions or the boundary conditions which are specified at initial points. So, for example, if you look at this, the two lines intersecting at 3.3, we know that if I am considering an arbitrary point 3, I can have two characteristics passing through it, one C plus denoted as C plus and the other denoted as C minus. Now, a priori, I assume that I know the properties at 1 and 2. What are 1 and 2? 1 is a point that the characteristic C minus characteristics has already passed through. 2 is a point that the C plus characteristic has gone through already. So 1 and 2 assume that I have the values for the gradients or the parameters that are required for the solution. Now, if so, I know that the characteristics that goes through 3 should satisfy these conditions as well as this, because it's common to or rather the other way around. Both these characteristics, C plus and C minus, should satisfy the conditions at 3 because they intersect at 3, right? So by considering this and knowing the values 1 and 2, we can do a solution. We can solve for, say, theta 3 in terms of theta 1 plus theta 2 by 2 and nu1 and nu2. That is, if I know values corresponding to 1 and 2 as theta 1, theta 2, etc., then I can calculate theta 3 and nu3, which gives me the values corresponding to 3. So, so in other words, if I start from two given initial conditions, I can calculate the properties of a point of intersection of those two characteristics. Now, once I know 3, then I can follow this. The same method can be followed, or rather marched forward in the direction of the flow. So starting from a set of initial values, you subsequently find out the intersection of characteristics and solve the points for based on those, and then carry forward the solution. That's a method that is used in the solution, and this is why it's a numerically demanding process, because we need to have first you need to have several points, several characteristics, and we need to have a flow net, that is a kind of grid or mesh that discretizes the domain, and then we need to be forwarding through the solution by carrying the iterative calculations based on the upstream values. And this is the method that is, and that's the reason why it is done computationally. Hand calculations probably do not make much sense. Actually, earlier it was being done so, but then the calculations were restricted to flow fields where you have relatively lower gradients, or you didn't have too much of a fine discretization for the flow field. And of course, when you have when you don't have sufficient resolution for the flow field, the accuracy of the solution also will be compromised. So that's why it is restricted. I mean, any like any numerical method, it requires a computational approach to solve for the flow field, unlike the analytical methods that we have followed so far. Now, what the formulation that we have discussed so far is only is for irrotational flows. This is also applicable in the similar way. Only the number of equations will be higher, because when you are solving for rotational flows, in addition to the two characteristics, the streamline also has to be solved for. So as shown here, so you will have the corresponding increase in the number of equations. At any given point, you have the two characteristic lines intersecting. And since the flow is rotational, please remember, when you have irrotationality, the flow can be mapped into a kind of a net, a two-dimensional net, if it's a two-dimensional flow field. Whereas when the flow is rotational in the sense the fluid elements can undergo deformation, then you need additional condition to solve for the location, the spatial location of the fluid properties, and that's the reason why you have to also solve for streamlines. So the two characteristics plus the equation for the streamline will be required while solving for rotational flows. So this is the method that is used particularly in hypersonic flows, where rotationality of the flow field is also important, and we cannot assume the flow to be irrotational. I'll probably skip the formulations for the rotational part, but then it's just a set of equations, and they're following the same method with the addition of the consideration for the sorry, streamline, considering the streamline also. And so in say when you have a typical problem in hypersonic flow, the way that the method of characteristic approach starts is by identifying discrete points, discrete cells within the domain, and then starting off with a set of initial conditions, maybe starting from the shock, downstream of the shock, where you can assume the initial properties and then follow towards by discretizing the flow field in between, you can do the solution in between. And the limiting the marching procedure is similar to what we have just. Only thing, it becomes more, as I mentioned, since you have to also consider the solution for the streamlines, the marching process will be more computationally intensive. So, but then the process or the approach is similar. You have upstream points on which the data are given, and then you use it for using the intersections to intersecting points for the or solving for the intersecting points of the characteristics. You march forward with the solution, and that's how you solve for the entire flow field depending on the discretization that you have. So this is the general approach followed in method of characteristics. I'll stop it here. If you have questions, you can take it. Okay, then we'll stop here for today. We'll continue next week. Next week I may be online. Sorry, yeah, I may be on leave. I guess we have classes on Tuesday and Wednesday. Tuesday is working. Wednesday is holiday. Sorry, Thursday and Friday are holidays, I think. So yeah, possibly Tuesday and Wednesday I will be on leave. So please note that I won't be engaging the class on. I guess it is 12 and 13, if I'm looking at the correct dates. 12 and 13, I'll be away actually, so we won't be having the class. Please make note. Okay, thank you.